Welcome everyone to another Control Meets Learning seminar. It's a great pleasure to introduce our today's speaker, Professor Munther Dahleh from MIT. He's the William A. Coolidge Professor of EECS at MIT, where he has been on the faculty since 1987, right after obtaining his PhD. He is the founding director of the MIT IDSS, the Institute for Data Systems and Society, and he has held many positions throughout his time at MIT, including Associate Department Head of EECS, Acting Director of the Engineering Systems Division, and Acting Director of LIDS, Laboratory for Information and Decision Systems. Munther has made seminal contributions to a really wide range of areas, from transportation and autonomous systems, to power grid, financial systems, and social networks, and in particular to network systems and robust control. And his work has appeared in many different venues, again, from economics and operations research to automatic control, biomedical engineering, network science. It's a really wide range of areas. His pioneering work has garnered numerous awards that are too many to list. Just to name a few, he has received the George Axelby Award 4 times, which is probably the world record, and the Donald P. Ekman Award for Best Control Engineer Under 35 in 1993. Today, we're going to hear from him about the data auctions with externalities. For the audience, if you have any questions, feel free to either post them on the chat or unmute yourself to directly ask your questions. So without further ado, let's welcome Professor Munther Dahleh.
Thank you, Naveed. It's a pleasure to be here. As a disclaimer, I wanted to just say that there is not going to be a lot of learning in this particular talk, although actually most of the stuff needs to be done directly from data, but I just thought that would be too much to present these ideas and to present the learning aspect of this. Maybe some other opportunities I'll present that. Decisions here are made in terms of multi-agent decisions and mechanism design, and so it is actually very relevant to this particular workshop sort of series. And in particular, the reason it's more relevant, it is directly about the data and the data that is acquired for learning and so forth. I have many collaborators, but this particular work is done with my 2 students, Anish Agarwal and Marianne Rui, and then my postdoc, Thibaut Harel. So just in terms of motivation, let me just say that obviously, as evident in this particular seminar series, data has become an exceedingly important commodity. Machine learning algorithms have turned everything into a data-driven decision of some sort. And I think the bottleneck in the next few years isn't going to be the question of, do you have the right algorithm, but rather, do you have the right data? And I think algorithms have become really great and distributed and fast and so forth. But then the question, do you really have the right data? And are you collecting the correct set of data? And this is a challenge that's going to happen, whether it's a slow process of data collection or a real-time autonomous vehicle that is just trying to figure out what is this thing in front of me. The data is going to be a critical part of every AI type solution. So I like this quote by the European Commissioner that says, "Personal data is the new oil of the internet and the new currency of the digital world." I think we have recognized that social data has become exceedingly important. Probably one of the most important reasons behind the previous revolution that we've seen is individual social data sets that have become extremely high dimensional and distributed and what have you, right? Today, however, if you think about data, it's traded, but in a very inefficient way. If you think about places like Bloomberg or Nielsen or Reuters, how do they sell data? I mean, it's very bizarre. They convince their audience to buy their data. Bloomberg, first of all, sets the tone, and then other companies follow. On one side, they sell data for operational purposes. Okay, so this is not data for machine learning. So for example, Bloomberg kind of powers the stock market, right? And so this is organizing the financial data, having it accessible. Nielsen does something similar. Operational data probably is easier to price. Not that obvious, but it's easier to price than, say, for example, you go into a company and say, I want to buy data about my customers, and you don't know how much you're supposed to pay for it. How much are you supposed to pay for that data? In principle, you want to pay the value this data adds. But then in general, we have very limited methods by which we can a priori say, how much does this data add? But this has to be the connection between pricing the data and the data itself. The data itself, as a bunch of numbers, doesn't really have any intrinsic value. It's only valuable in the way you utilize it and use it. So this lack of efficiency demands a need for a market by which this data is created. And so the other aspect of this is that, and just another example, I mean, there are just a ton of examples to make this point. When we had the Equifax data breach, for example, there was about 150 million data sets that became public. And I think this is a really interesting question. Probably your data set and my data set were part of this particular data breach. And I'm not really sure it affected me at all. So, what does it mean for 150 million data records of financial data becoming public? What does it mean? I'm sure somebody took advantage of this, somebody utilized it, and different than when the stock market in 2008 collapsed, we could say this cost us certain billions and trillions of dollars. This data market or this data acquisition doesn't have a dollar value next to it. 150 million financial record doesn't have a dollar value next to it. We don't know what the damage is. And a similar example with Cambridge Analytica, where we know, for example, 2016, Cambridge Analytica intervened in the election. We don't know if they impacted the outcome of the election, but we know that they intervened in the election. So to a certain extent, what is the cost of that intervention? So these are all important questions about the value of data in general. And there are many other examples. I'm not going to go into that, but I want to mention one particular area that we're working on in sub-Saharan Africa, where we're interested in development economics for farmers. And the idea, can we turn farm data and farmers' data into an upside in terms of their economic growth? How can we use that for better intervention so that we can up their value proposition and sort of have them produce more and more profitable products? And it's predicated on them sharing their data. And the question is, what incentives do they have to share their data? Why should I share my data? Why, if I am a farmer with a secret sauce, why would I tell my neighbor what I'm producing? I don't have that incentive. So a data a platform that incentivizes you to participate is critical for this data to come back and actually benefit you. And of course, we know this stuff in genomics, we know it's in finance, we know in digital ads and so forth. So, and one comment I want to make is that as part of this introduction is that we see a lot of different markets. Okay, I mean, we certainly are very familiar with the stock market, and the stock market at a very primitive level is a sort of a matching market. Stocks post a price, and then other people kind of post their price, and then there's a match, and when there's a match, there's actually a clearing methodology. These are markets we're very familiar with. We start creeping into the world of digital markets when we think about ad auctions. Now, ad auctions, have been studied a lot. I'm sure a lot of you have heard talks about how to do second price auction, first price auction, that kind of stuff. But and auctions are still not data in the sense that what your ad auctions, what you're selling is a piece of real estate on the web browser, and that in itself is a product. I mean, it's something that is tangible. So it's a little different than a data market. But behind the doors in ad auctions, there's a lot of data markets that are being, there's a ton of data that is being sold by different organizations. And I won't get into the detail of that, but this does connect The background of ad auctions does connect to the story that I'm going to tell you today. And then going to the right here, prediction markets is probably the closest to a data market, because a prediction market is essentially a market where you place your bet, you assign a probability distribution on an outcome, who's going to be the president of the United States, and you win some money if your outcome is right, okay? In some sense, you sold your data and you got paid for the good outcome. So it is a data market. It's a very aggregate market in the sense that you're selling your predictions directly. You're not selling raw data that you have, you're selling your predictions directly, but that's not in itself a bad way of thinking about a market. Here, I would think maybe prediction markets are more like crowdsourcing than it is about a market of data, okay? But it is definitely one example of a data market. Here's how I visualize what we want to have, okay? I'm going to give you an example that comes from a logistics company, okay? So in this case, what you have is two types. You have the buyers and you have the sellers, okay? The buyers are the logistic companies, and they come to the market to buy data so that they can improve their prediction of inventory. So multiple retail companies, they want to know what to stock for the back to school season, and they're trying to understand what's going on in the world in order to stock. Now, of course, they have historical record of all the data that they've had before, right? That's real thing. What's the demand has been previous years, but they're looking for additional data that they may not have, okay? What is this additional data? Well, it could be, for example, trips to the malls and shopping centers. How often are people traveling to shopping centers? Well, kind of an indicator of what's going on in the economy. Movement around cafes and spending. So are people actually spending more money? So there's a question of, again, as an indicator of economy. They may be interested in crisis and so forth. They may even have people's reactions on Yelp or group or other platforms in which they're rating things or saying things about what they want to do and what they're interested in. So that's the seller. And the market in the middle, the marketplace, has the job of taking this data and giving it to the buyer. But the problem is, of course, you can't give all the data to the buyer because the buyer has to pay for something. And the question is, how do you define a mechanism or a market that you can actually sell data? Well, the key observation and important issue is that the data only matters in the way it provides accuracy to the buyer. So the buyer comes in and tells the market, I'm interested in this prediction task. Okay, so now we have focused the attention of the buyer. It's not like I'm buying data. I'm buying data to improve my prediction task on the back to school season, very specific. And I'm going to compute that using regression or neural network and so forth. And I have this data that I'm starting with. The market then can evaluate the increase in accuracy through some machine learning algorithm. That increase in accuracy should mean a dollar value for that particular buyer. For every 10% improvement in the accuracy of prediction of inventory, they save X amount of dollars. That's what we call the valuation of accuracy. So the buyer comes in and has a valuation of the accuracy. And that's a very important point in defining where the dollar value starts appearing in the sale. Okay? So then, so the market will set up a mechanism in which the buyer is going to come in, maybe will bid for the data, will bid for accuracy. It's not going to bid for data. It doesn't care which data you give them, but it will bid for accuracy. For every amount of accuracy you give me, I will give you this amount of money, okay? Then the market collects all of this money and then goes back to the sellers and give them the collected revenue. And the collected revenue has to be divided among the sellers. And that's another complicated exercise because not all the sellers contributed to the accuracy the same way. So not all the sellers ought to get the value of their money. So, now you're going to see that in this particular talk, I'm going to be ignoring the side of the seller because it gets a little complicated. So here's sort of the summary of this motivation introduction. Why is this a different problem than your usual multi-commodity, multi-firm sort of mechanism design problem, there are some aspects to it that is interesting. One is the data or prediction can be replicated at zero marginal cost. In other words, the same data can be used for multiple people. Okay, so you don't have budget constraints as you're allocating your information or the data. So kind of we viewed then the problem as an information design problem as opposed to a selling of a commodity. The way the data impacts the accuracy can be of a combinatorial definition, right? So, you know, any subset of data could provide a certain amount of prediction, so the relationship is combinatorial, so the computation is really prohibitive. The reasons companies come to buy data can be very different. So yes, I did talk about logistics, but, you know, logistic companies may come in to buy data for different reasons, maybe for different prediction for different time frames or for different products, right? But in general, in a market of data, maybe companies are coming for totally different reasons, right? So prediction tasks can be very heterogeneous in nature. Of course, authentication of the seller's data and understanding what it means is also important. That's kind of more of a computer science aspect of this. And finally, the valuation of the firm can have externalities. You know, if you think about two independent firms that come in to buy data, you know, yes, I want to get better prediction on my market, but actually, as you get better and better prediction on your market, you affect me negatively. Because as you do better, I do worse, you know, because it's a competitive market. We're both going to go down on a downstream market to compete with our products, and that's a competitive market. So there's an externality effect, which makes the problem somewhat difficult to analyze. So those are the aspects of these data markets, motivation and features of this problem that we're looking at. Okay, so what I want to do is sort of begin to focus the problem a little bit into an abstract formulation from where I was, and then kind of give you an idea of the solutions to this problem. Okay. So let me go back again to the formulation. This got screwed up when I made the PDF file. Apologies for this. Okay. So so I'm going to think of this. This is the general problem, and I think it's an important effect that I want you to capture here. So in general, I have a market, right? I have a consumer who have data that I'm selling, and then there are firms that are interested in buying this data. Okay, so the added feature I'm putting in this particular model over here is that the firms are buying data from the consumer in order to design a product for the consumer. So think of it this way: consumers may be having genomic data. A company like 23andMe plays as a market. Okay, 23andMe then can provide this data to different pharmaceutical companies who are then designing the products, namely the say vaccines or medicine, to different consumers. Okay, so so this is how the market senses this information from the consumer. So there's a market happening over here. Consumer is selling to the data market. Data market is selling the data to the firms. Okay. Now, because of the combinatorial aspect of the data into accuracy, so as I said, the data buyers are interested in the accuracy, and because of the combinatorial aspect, I'm going to remove this link over here and just say that already the data intermediary knows how to allocate the accuracy. How the accuracy maps combinatorially to the data sets, I'm going to deal with that some other day. Okay, so combinatorial data sets translate into some accuracy for each firm. The data market or the intermediary sells the accuracy directly to these firms. Okay, so because of that, I'm going to actually, this is what I just said, I'm going to assume that I'm going to sell accuracy directly, and as a result, now the data intermediary is just allocating accuracy. I'm going to normalize it as a quantity between 0 and 1 and say you are going to buy from the market an accuracy between 0 and 1. How we get that in terms of the data and the machine learning algorithm is some other topic. Okay. So that's now the picture. We killed this part over here. It's gone. And now we're going to focus on the firms over here, buying the data from the data intermediary so that they can compete in a down market. Okay? So in some sense, there are two types of games that are ongoing. The firms are playing a game in a competition market against each other. This is the talk is all about externality. So maybe it's a monopoly or oligopoly that is ongoing. We're playing a competitive game in the downstream market, okay? But then there are hidden states, namely the accuracies about, this quantities about the market itself that we don't know, but the data intermediary knows. And so I would like to go in another game, auction these things, play in an auction, get information about these variables so I can play in this downstream game. So it's a complicated two types of a game. I go to the auction, I buy some information, I come to the down market, and I compete in the down market. How am I going to actually figure out how to do this particular problem? Okay. So let me give you an example. Okay. I'm going to do something else because this, the equations got disappeared from my PDF. So I'm going to stop sharing and share a different, sorry about this. I don't know why that happened. It doesn't happen often. I didn't check it, okay? But I'll do this. I share. Sorry about that. Give me a second. Yep, okay. Okay?
Okay.
All right. So, yeah, thank you. Sorry about that.
No worries.
So now what I'm going to say is that I'm going to justify this picture that I just gave you in an example. The example is going to be, and so that I can motivate the model of externality that I'm going to use, and then I'm going to summarize some of the results, okay? So let's just think of the firms playing a corner game over here, okay? So what they're interested in is the two firms, only two firms, they're playing a corner competition game. Okay, so what they are deciding is the amount of different products that they're selling. They're not exactly substitutes and they're not exactly complementary. There's some relationship between these two products, but they are going to decide the quantity Q1 and Q2. Okay, and then there is a model, and I just removed the cost and all of that from this model. But the point is that there is a demand model, okay, and the demand model dictates the revenue that I get. Okay. Well, let's suppose that and so I'm not getting into this corner game. I'm assuming that you've seen this before. But the point is that based on this demand model, and this is the important thing, the profit I make, okay, depends on what I produce, how much I produce, how much the competitive firm produces, and two parameters, alpha 1 and alpha 2, that appear in the demand model that indicate the preference to certain types of products, okay? Let's say that there is some uncertainty around these, and I can do better by going to a market, an intermediary, and buy an improvement on these alpha i's. If I buy an improvement in the alpha I, then I can actually improve what I produce, and I will get more revenue or more profit. And as I said, there is a cost which I ignore. Well, just abstractly think that what you're doing is you're adding an information. So it's a very simple additive model. So there's an amount xi that I can get that modulates alpha I. So I can buy x1, an accuracy for me. My competitor can buy x2, an accuracy for them. And I want to see how much my profit changes as a function of x1 and x2. And if I assume just a local world right now, so I'm not really interested in a huge variation. Alpha I is fairly well understood on my part. I'm getting a small variation on that. I get some sort of a linear model around through a linearization. I get a very simple linear model that describes this utility, okay? And this is the motivation behind my linear model that I'm gonna talk about. So what happens is that I get the amount of accuracy I bought for me is multiplied by a valuation which is positive. So the more accuracy, I get more value out of it. And the amount of valuation my competitor got multiplied by a negative quantity, which means that the the more my competition knows about the market, the less utility I get. So this is a negative externality. So I have a positive externality through V1, negative externality through eta. In this local model, I can argue that we have a valuation that looks like a linear model. VIXI for each valuation of any allocation X, I get from it my own VIXI, but I have a negative externality from the allocation from all the other guys, the other firms, okay? So the problem then becomes this particular linear problem description, and that motivates our model to say that, okay, we have n firms, okay? Each firm, so now the market, so what's gonna happen is I'm gonna ignore the downstream market, because the downstream market translated into a simple linear or a simpler linear valuation function. So now I'm going to ignore the downstream market and I'm saying, look, I'm going to compete in this auction. Okay, in this auction, the valuation I get for any allocation X, remember, X is an accuracy allocation. It's allocated to every firm. Okay, that what I get is my part of it minus everybody else's allocation. Okay, so now what the market needs to do is to set up a mechanism, an auction mechanism, for which it can actually perform this purchase. And I want to talk about the properties of this allocation. Okay, so the picture really goes, this is the negative externality, this is my own allocation. So as I said, so what is the market going to do? The market needs to figure out how to define this mechanism. So what is a mechanism? The mechanism is an allocation function, which we refer to as X of T, where T is a bid. So this is an auction. We're going to have the buyers, in this case, the firms, bid into this auction something. Then the market will allocate X to them, the accuracy, and we'll have them pay P of T. That's the amount of money they pay. Okay? The private information that the firm has is its these parameters, VI and eta IJ. Okay, in the general sense, the market, one can assume that maybe each node, each firm I can know VI, eta IJ, and eta JI. That is how it affects other firms or how other firms affect it. You can also argue that it only knows how it affects other firms, but not how it's affected. Or you can argue that it knows how they affected, but now how it affects other firms. So it's either you know eta IJ, or you know eta JI, or you know everything. Okay, these are different information structures. Market design depends on the information structure, but I'm not going to go into all of these cases. I'm just going to take one case and analyze it. Okay, okay. So bottom line is the private information is the knowledge of the valuation. So the bids is going to be bids on the private valuation. The market is going to set up a bidding exercise where you bid your private valuation. So how does the market do that? So now we enter the exercise of mechanism design. Okay, how do you design something where people are incentivized to bid a truthful set of values? So let me get into that a little bit. Okay. But then what you're trying to do is really define an allocation to optimize some objective function. These objective functions typically are either, price, like you want to collect as much money from the firms, or you may be interested in social welfare. We can look at both of these situations. That's the standard process, okay? All right. So at this point, what I'm going to enter is a bunch of technical stuff about optimal auctions. Okay, there's going to be a lot of hand waving and few theorems, and then I'm going to give some results and then try to kind of give you an insight about these results. Okay, so what is the, again, let me just repeat, an auction design, you want to design an allocation X of T, where T here is the bid. Okay, in our case, usually what you bid is a private information. Okay, in our case, the private information to the firm is its valuation and the negative externality parameters. So it's a vector VI and eta IJ. So the market designs X of T, a way to allocate. For a given bid, you get something. It designs the payment function maybe to optimize welfare, and welfare means you just want to add up all the valuations. So however, add up all the valuations for all the firms, or you want to maximize expected revenue, so you add up all the prices that you collect. Okay, these are the two standard approaches for doing things. Okay, we want to design these things subject to truthfulness and participation constraints. What are these means? It means that what we want is a way the mechanism is designed. Since this is private information, the market doesn't know it. Because the market doesn't know it, it cannot allocate by optimization. It cannot optimize the allocation based on what your private, what your valuations are. So it has to elicit that information. So the mechanism has to elicit that information. So how do you design it to elicit that information? That's a truthfulness constraint. And then, of course, participation constraint is important. That is, every firm needs to feel that they are incentivized to participate in this auction as opposed to stay out. They're not going to lose by participating. They do better by participating than not participating. There's always a difficulty in this because when there's externality, participation, you can still participate and end up with a negative utility. You know what I mean? The point that because I sold information to your competitors, you may end up with negative utility. You may actually not get allocated any additional accuracy, end up with negative utility, and still be incentivized to participate in this auction. So it's an important thing that individual rationality, which I'm going to ignore in this talk, but it's in the paper in gory detail. Okay, so the market does not know the private valuations. That's very important. Private valuations are owned by the individual firms. And as I said, the way we set up the market depends on the information structure. So I'm going to come back to that. Okay, there are n variables to be allocated, and these are the discrete, the x sub I, where x sub I is the accuracy allocated to particular firm I. Okay. So as a quick crash course, how do we solve this problem if there were no externality? Okay, because externality couples the relationship between all these firms. But what if I didn't have the externality? How do I solve that problem? Well, okay, that means that each firm has its own valuation VI for the allocation, but has no effect on the other firms. They don't affect each other. There's no externality. So the fact that I get allocated something doesn't have any negative effect on the other firms and vice versa. So the eta IJs are equal to 0. Now here's something that is really interesting. This is a simpler problem than the usual mechanism design problem because there is no budget constraint. So I can allocate whatever I want to any firm. I don't need to satisfy a budget constraint, which means that this translates into n independent auction problems. Okay, each firm is separate from the others. I solve the problem for each firm. How do I solve that problem? Well, that's just a standard mechanism design problem. So just a quick review. I just think about one firm. I'm trying to allocate an accuracy to that particular firm. I'm either maximizing welfare or maximizing price. Okay, revenue that I'm generating. Okay, well, welfare is just V times XV. XV is the allocation, and V is your valuation. And we're assuming valuations are drawn IID from an underlying distribution. For the time being, we're going to assume all of these distributions are known. This is where the learning part of this problem comes in. Okay, so the maximizing expected V times XV is the social welfare. Maximizing expected value of the revenue generated is the optimal pricing, optimal revenue maximization. But now I'm only having one firm. Everything is really simple. So how do I do this problem? Kind of comes back to sort of Meyerson's sort of idea, and it's fairly straightforward. Okay. So the first thing we know is that a mechanism is truthful. A mechanism, it has an allocation, is truthful. It has one parameter, namely V. Okay. If every bid you have V hat, you're always better off bidding your truthful value than any other value. That is your utility under this mechanism allocation and the price that you're collecting, that you're paying, your utility is higher with the truthful value than with any other value that you can bid. So that's the definition of a truthful bidding. And Meyerson gave this result that said that basically a mechanism is truthful if and only if two things have to happen. XV has to be monotone or non-decreasing in V, so higher bids imply higher allocation. And the price is determined by this integral equation, which is essentially a bit of this equation, which essentially says you pay, the amount of pay is really the incremental revenue you generate. So it's VXV is the utility minus any utility you would have had if you bid any lower value. So you get VXV is the full rectangle minus whatever you would have got if you bid any smaller value. That's integral V x of V tilde d V tilde, right? So that's Meyerson's formula. You find x of V, first of all, as a monotone function, and you plug into this formula for the payment, you get a truthful mechanism. The only thing that is required here is that this particular mechanism has single parameter V. Okay? So that's actually a very powerful result. It allows us to right away solve the problem of the one agent. It's not that hard. So what we're doing, we're solving, okay, so the first case is fairly straightforward. You're doing social welfare. Well, social welfare, I mean, you're looking at the allocation, V times XV. V is always positive, non-negative. So whenever V is non-negative, give XV the whole thing. So make XV equals 1. So the allocation is the indicator function for V greater than or equal to 0. Anytime V is greater than or equal to 0, give X the whole thing, you maximize the allocation. And this is clearly a monotone policy, and that's the maximum you could do, right? So that's the optimal policy. So what does it say? It says, trivially, for maximum welfare, give everybody everything. So give the firm all the information at 0 price. Firm will be very happy. We're not maximizing revenue, so we don't care. And the firm is happy by getting all the information. Okay, so max welfare is a trivial problem in this setting. And I'm doing this just to kind of set up the full solution. If you're trying to maximize revenue, then there's a trick also by Meyerson's auction. And the trick is as follows. You're trying to maximize expected value of the pay. The pay, remember now, is given by this formula. Then you can just do some maneuvering, and you know the distribution of V, and you rewrite this as the expectation of XV times what we call a virtual valuation. And the virtual valuation is a function is obtained from the cumulative density of the distribution of V, which I'm assuming is common knowledge. Okay, so then what happens is now the optimal allocation says XV should be 1. You give everything, give 1. Whenever this quantity is, whenever the virtual valuation is positive, and you give 0 when it's negative. Okay, you get the maximum revenue allocation by allocating XV positive for V. So it's a pointwise solution and it's optimal. And so basically it says whenever PV is positive, you give everything, and that's the allocation rule. So the allocation rule is fairly simple, which means that you have a reservation price. Essentially what happens, V's are coming IID. If V comes up to be larger than phi inverse of 0, then you allocate 1 to them. And if V comes in less than phi inverse of 0, you allocate 0 to them. And in expectation, this would actually give you the maximum revenue generated. So not everybody gets everything. It depends on their valuation, and they pay this price for it. And interestingly enough, you can just easily see that phi, this virtual valuation of V, so the valuation could have been, let's say, a quantity between 0 and 1, but then phi of V can be negative and can be positive, right? So if it's negative under 0.5, this is a regime where you do not allocate any accuracy. So a firm comes in, it has a low valuation, lower than phi inverse of 0. In this case, it's a uniform distribution. Sorry, I didn't say that. This is a uniform distribution. So it's just half. So if you're below a half, sorry, you don't get any accuracy. If you're above half, you get the full accuracy. This is the maximum revenue, even though it's actually not allocating as much as the social welfare. Allocates less, but gets more money. Okay? So that's the mechanism for the no externality case, easy case. Okay, so just very quickly, I want to summarize the solution for the case with externality to say that, okay, but I mean, we cannot treat the firms all separate from each other. We obviously have to connect them with each other. And what I'm going to say is that, as I said, there's an information structure in terms of what the firms know. Do you know how you're affected by others or how you affect others? And of course, you may know everything. That's another case. Let me just, kind of give you a sense of the idea of this and then just give you the result because there's not enough time to go through all the proofs. Let's just think about the social welfare case, right? Social welfare with externality, I'm going to try to maximize the sum of all the valuations. Okay? Sum of all valuations is the sum over all firms of VIXI minus the externality, XG. I'm going to sum them all up, rearrange the terms, and write them as whatever term that multiplies XI. And I get this summation over I, this term multiplying XI. So now, to maximize pointwise this quantity, it's fairly simple, right? I will make Xi 1 if this quantity is positive. I'll make Xi 0 if this quantity is negative. I get the maximum value. Okay? So Xi, again, right, because I'm maximizing the social welfare, Xi is any number between 0 and 1. Makes no sense to give any value but 1 when this multiplier is positive, and you give 0 when the multiplier is negative. The interpretation of this multiplier is really nice and simple. It says that you are allocated accuracy when your valuation exceeds the negative impact you have on everybody else. And when you benefit more than what you create harm, you get Xi. If you create more harm than benefit, you don't get the accuracy. That's the social welfare solution. Fairly simple, right? And then you can show that, in fact, that actually is optimal. And I can show just with a flash with my hand here that I can solve the maximum revenue problem by using virtual valuations, the same way I did in the case of one person. I'm going to go through the exercise, but it turns out to be exactly the same. So this is the welfare maximization I just talked about. VI has to be larger than the negative externality. Here, the virtual valuation has to be larger than the virtual negative externality. Okay? Fairly straightforward interpretation that comes from the same thing that we have in the single case. Now notice what happens is that phi of VI is always less than VI, and it can be negative. If you take phi of a negative quantity, it gets more negative. And so in some sense, what happens over here is a lot less allocation than here. It's a lot less allocation. So in the maximum revenue, always you're allocating less and you're collecting more money, which is also a phenomenon that happens. But this is actually a formula for how the allocation occurs. It's actually a clean formula. And the nicer aspect of this is that the payment function, and I'm skipping all the proofs and the interpretation, just giving you the interpretations of the result. The payment function that you pay is actually have this interpretation. So you can write down, okay, so here what we assume, even though we have n parameter auction, because you're auctioning not only your valuation, but also the negative externality, I did assume an independence between VI and AIs. Okay, so they're all independently, so they're generated by an independent relative variable. Okay, that's an important assumption here. Okay, so what does the pricing look like? Okay, so it seems that I'm going to pay, what do I pay the auctioneer? What do I pay the market? I got, for any bid I give, I pay them the allocation you give me times, not my valuation, but take my valuation, take the bid I gave, the first element in it is VI, reduce VI to the point until I no longer get the accuracy, and that's tau sub VI. So it's the smallest bid for which an allocation happens. So I pay that, Xi times that. Then I pay for all the people that I caused not to get an allocation. So for every xj that did not get an allocation, okay, I pay, again, the smallest value of the bid that I would have had to cause them not to get an allocation. So I am paying for my allocation, but not in terms of the valuation I get, but the smallest value that will make me not get that value, the accuracy. And then I go to every other person and I pick something for each person I cause not to get the accuracy, xi, and I pay a constant in addition to this. This is an interesting quantity here. So there's a very interesting interpretation of the pricing. Again, all of this Myerson stuff is generalizations of the second price auction, and the residual pay is a second price auction sort of idea. But this is, of course, multi-agent. With externality, the pricing is a little bit more complicated, but it has this interpretation. Now, the last piece of this pricing is this constant. This constant is optimized by the auctioneer, and it's actually CI is a negative quantity, so you're adding this amount over here. So what is CI? Well, CI has this interpretation of being an entry fee. We come into this market, and because of this CI would be 0 if there was no externality. CI is 0 with no externality. So when there is externality, not only I'm going to charge you if I allocate, I'm going to charge you to just come into the market. Okay, there's a fee for you to enter that market, and you still be individually, the individual rationality condition be satisfied in that you are better off to participate even after you pay this entry fee. And the explanation of that comes from this entry fee really is the sum of, it's dependent on the externality amount. So let me just tell you a little bit about this particular case. So if I assume that my valuations are drawn from a uniform distribution, okay, and I fix my externality AIG, okay, then I can show you that the total revenue has a formula in this case. It's really simple. And total revenue collected is the sum of the externality, summation over j, not equal to I eta ij, if this quantity is larger than the support, and then some other quantity if it's less than the support. Okay, the most important thing about this formula is that Ri actually depends on the sum of externality. It increases as the sum of the externality increases. Okay, so the revenue collected by the auctioneer increases when people have more negative externality, when the competition is much fiercer. The auctioneer can make more money. Of course, remember, the auctioneer is an intermediary that was collecting the money so that they can pay the sellers, which I removed, right? So the sellers can make quite a bit of money if the competition in the market of the buyers is high. And the point here is that actually this price is related to the EI, right? So a very interesting observation from this type of solution is that auctioneer can make quite a bit of money in the existence of a competition, which is really a nice property here, saying, your data has become extremely valuable because there's a high competition between these firms. When there's not much competition between the firms, actually your data is not as valuable and it doesn't increase in this particular way. Well, it is valuable, but valuable individually for each firm. Externality doesn't get into the picture. And I said several times that the allocation in the case of maximum revenue is a lot less than the allocation of maximum welfare, so I don't want to spend time on this. Okay, so I just want to conclude by giving an example. Okay, so this basically a body of results that Marianne and Anish and Thibault sort of derived in that paper on all possible information structures for linear auctions. Okay. And I gave you one example of that. So you're more than happy to look at, can give you a reference to the paper. But the interesting thing is back to the modeling exercise. Remember how I came to this problem is I said, okay, you're competing in a kernel competition in down market. Locally, that looked like a linear problem. Let me solve a linear externality auction. That's what I did. But what if actually that competition in the down market doesn't have this local behavior? I cannot linearize the problem. Then I need to solve these two layers of games at the same time. The problem gets substantially complicated. So let me give you an example of how you think about it. So back to this setup. A prototypical example is called the hoteling problem, okay, or concentration problem. So essentially what is happening is that this is a distribution of how people live, okay, where they live, and X is unknown. Okay, it's known to it's a hidden state of the world. There is say an oracle that knows X, but the individual people don't. Okay, so the oracle knows X, but it's unknown to us, and we're trying to build two restaurants. Okay, so Burger King and McDonald's are coming in to compete. They want to place themselves in this world, right? But they don't know what X is. Okay, of course, if you think about the action, if you put yourself in Z1 and Z2, then take the average between the two, and what happens is that Burger King will get this market share and McDonald's will get this market share, right? So it's very important to know where you place yourself to actually get the maximum market share in this game. Okay, what is unknown to you is X, so that's a problem. So you don't know where to place yourself. And of course, maybe we can argue that Burger King is more of a classier restaurant than McDonald's, so their valuation could be different, right? So you take market share and multiply by some valuation. Valuations can be different, but market share is a zero-sum game or a constant sum game. Okay, if I get something, you get the complement. Okay. The problem with this is that X is not a local behavior. X could be anywhere in this Gaussian distribution. And so the range of X is very large. My linearization algorithm and so forth in the corner game would not work, and this would not be motivated by a locally linear problem. Okay, so what happens? So let me then kind of blink and turn this problem into a discrete problem where X could be in the far negative, and I call that 0, or X could be in the far positive, and I call that 1. And the game essentially is that the two players want to align themselves with X. I mean, ideally, what you do in this game is that both of you will align yourself with X. If you know where X is, you build next to each other. One person gets the right, the other person gets the left. That's the optimal solution, okay? Well, you don't know what X is, and you have a game, and this game, both players are dominated to play the same strategy. So if X is equal to 0, then the first player plays 0 and is a dominant strategy. Second player is a dominant strategy of 0. If the state of the world is 1, then both have dominant strategies of being 1. Okay. You may want to say, I don't know what X, so I solve a Bayesian problem. Well, in the Bayesian problem, if I assume that the probability, say, for example, 0 is higher than 1, then everybody will play 0, 0. That's the Bayesian solution, right? That it's kind of simple, right? But now I want to put the layering auction on top of it and say, well, maybe you can go to this oracle and buy information about X. Get more information about X. How much are you willing to pay for this? Of course, you have different valuations. Valuations is captured here either by 0.5 or 1, right? But how much money am I willing to pay, for this? That's the interesting question. And what is the auction mechanism? So anyway, we describe the auction mechanism. We put all the constraints for truthfulness. And this is a problem which is really simple, but it kind of exhibits phenomenon that is very different, right? In the case, as I said, of no information, everybody plays 0, 0. It turns out that if your valuation, and the valuation here are going to be sampled, this is a numerical solution, so sampled between 1 and 20 values, just numbers, right, in the example that I have. If you actually are between a lower bound and upper bound related to your distribution here, both and the mechanism, okay. So another piece of information is that you can actually show that the auctioneer doesn't have to tell you noisy information about X. It can actually tell you what to do directly. It becomes equivalent problems called the revelation principle. So instead of giving you information about X, I can tell you, go right, go left. Go to the 0, go to 1, okay? It's equivalent formulation. So here's the interesting thing is that, okay, there's a certain range of valuation to both players where the auctioneer will tell them the right thing. Play 0, 0 in the case of 0, or play 1, 1 in the case of 1. But once one of these guys' valuation exceeds a certain value, auctioneer does something really bizarre, right? So here now, in this range, the auctioneer, now the first guy valuation is much higher than the second one, or higher than the second one. It comes in and says, look, for the first guy, you play the right game, you go to 0, But for the second guy, he sends him to 1 and does the opposite in the 1 situation. This is sort of a phenomenon that we call obfuscation. It's not that it settles for saying, oh, you just both play 0-0. It sends the guy with the higher valuation to 0, but sends the guy with the lower valuation to the wrong place. And by sending him to the wrong place, the market collects more money. Okay? And so, but the problem is that these are individually incentivized to participate. So one of these players couldn't not participate. I mean, it would have been better off. This player would have been better off not to participate and just play 0, you know, in this particular case. But the problem is that they couldn't not participate and the first guy participate. And so there's a result of these types of problems of obfuscation, which is a kind of seems problematic in terms of the market, but it also highlights some of the really interesting properties of these information design problems when you have, when you're solving 2-layered problem. One is a correlated equilibrium and the other one is an auction on top of it. Okay, so I'm done. I think I'm just gonna quickly say that yeah, so I'm just going to say that we're still focused on trying to understand this particular problem over here. I didn't spend a lot of time talking about this flipped. Yeah, okay, sorry. So the seller is now on my right, not the buyers. This is the part where I ignored, and this is the part, this range is the one I've been focusing on, but we focus on a problem where there's linear externalities and linear cost, sort of valuations. That problem is essentially solved, but when you bring in the downstream in a way that is not local, the problem seems to indicate a lot of complexity in terms of place computation on one hand, but the other one is the characterization of what the optimal mechanism look like. The example I gave you shows that we can do this example, but we are still working on generalizing this in terms of the property of the original problem. And okay, and I'll stop here. Thank you.
All right, thank you very much, Munther, for that interesting talk. Very insightful. If there are any questions from the audience, please feel free to unmute yourself and ask directly. And I have a question myself too. You sort of mentioned that basically that there's a learning component that we didn't talk about here. If we bring in learning, how would that interact with the market design, with the mechanism design aspect?
So I think that the way we want to think about the learning is that we start tracking. So what is happening with the mechanism design is that we know its structure, right? But we don't know the parameters. So we know that you allocate, let's just take the simple linear case. So you're going to allocate if your individual VI is greater than the negative externality, right? So what would happen is that people will come in with their bids, okay? And we run an algorithmic game problem, right? Where you come in with the bids, we implement the design, we collect the price, and then we do some sort of a no regret update every time in terms of how we either update our prices or how we update our understanding of the distribution that's generating these valuations, and then also the individual valuations. So we've done this algorithmic game in a simple case with no externality. And so basically what we'll do is just people come with their valuations, and then based on the valuation, we just implement the strategy, and then we see what happens. But we haven't done it with the externality. There's just some complexities that arise in terms of what you're learning and if what you have is learnable or not. So, but basically, there's been quite a bit of work actually in showing that so mechanism design can be really complicated, right? Just satisfying the set of conditions for a mechanism to be truthful and individually rational, so it can be very complicated. But it's been shown that the complexity does not increase by trying to design it directly from data, which is sort of interesting. That there's just a mapping. Whatever you do in the problem itself can be done directly on the data set. But we haven't done the learning. But there's a lot of learning. The way mechanisms are learned is that you run the market, you allow people to bid, you allocate, you see the response, and then you keep updating, and you see where these things go.
Right. Great, thank you. Any other questions from the audience?
Hey, Munther, thank you so much for this talk. I have a very, very high-level question. How do you think the privacy and fairness will influence this auction process?
So actually, a really interesting question. So fairness is a separate question. I'm going to put fairness aside, but privacy is critical to this, right? Because privacy has been a very complicated notion of what do we mean actually by private information. So, you ask yourself the question, is my genomic data private? Okay, it's a really interesting question. I mean, do I think my genomic data is private? You can say, yes, absolutely. I don't want you to take my genomic data. Then I come and tell you, okay, what if I paid you $10,000 for your genome? Okay, now I'm going to think about it. Maybe it's not that private, And what if I told you that your genome is going to solve this cancer problem? Then maybe I'll just give it away for free, right? And so we've been talking about the privacy of data without recognition of what the data is being used for. And I'm saying here, when the data is being communicated in a market, so nobody takes my data, I come to the market to contribute my data, I will recognize the value of my data in that market. I can put a threshold and say, if my data is worth less than $5, I'm not selling, but above $5, I'm selling, And privacy all of a sudden translates into a dollar value. It seems like, that's an economist's view of the world. But actually, in my opinion, entirely the conversation about privacy is not well-founded because we do think of the economics of our value. We think, for example, as I said in the genomic example, it's always interesting. I contribute, 23andMe can take my data. Now they have built a repository of amazing genomic data. They may discover some rare disease, okay? And then the rare disease results in higher insurance for me because I have it, okay? So, then I would say that was a mistake participating in this market, right? Because the outcome of this cycle resulted in more pay. In fact, I already paid 23andMe to give them my data. That's a great market anyway. You pay to give, but you paid to give your data. Then you actually are bitten by the backstream market. So I'm saying if I could look at this market and recognize that in fact it's a positive for me because I contributed, then I may contribute this data. So I think that actually data markets are going to hit this privacy question on its head. Translate exactly what the value of your data, and then you can decide not to contribute it. And people should be happy that you're, so now that's one thing. The second problem, that's really why this question is really important, is the externality among the sellers. So now, the question about your privacy, how private are you? So let's say that we're office mates or, we're friends in academia and so forth, and I decide to sell my data. I already gave enough about you, because of this relationship between you and me, and so you almost have no choice. You have to prevent me from giving my data because my data is correlated to yours. And if I say something about me, I've said something about you. Actually, by me saying something, your data become less important. I got paid more than you because I said that first, right? And so the correlation and the externalities among the data sellers is going to play an important role. And today people tell you, oh, I don't need your data. I have your data. I have it in terms of your brothers or sisters or, So, but it's even broader than that. I can have the data about the category I'm in. So that's a really critical question. The fairness question, I think, I have a different opinion about that has to do with more causal inference, but that's not the topic of today.
Thank you.
Okay, we are running a bit over time, but there is a question in the chat. It says, what about competition between different data markets that will affect the mechanism design and the mapping from data to accuracies? Is that true?
Yeah, I think that's a really interesting question. I haven't thought about this. I mean, I have been asked that exact same question before, but we haven't come up with a formalism where you have multiple markets where you can sell your data to and potentially create a competition between markets. Remember, you can sell your data to multiple markets if they existed, because you can sell your data to an infinite number of markets. But this competition does have, we're trying to do a case study on music as a digital good, and try to understand how different platforms competed, where we went from selling tapes to selling CDs, where I remember times where I paid $15 for a CD that had 8 songs, right?
Right.
And I'm that old. And then how all of this stuff now changed into a service model, in terms of purchase you never own, but you rent and you're paying a service fee. And there were multiple platforms in there competing. So trying to get a sense of evolution of how this happened. But I don't have an answer to this question. It's a great question.
Okay, in terms of, I guess, in the interest of time, if there are any other questions, I guess you can later ping Munther.
Yeah.
So thank you so much, Munther, for the excellent talk. Thank you so much, everyone, for joining us. And
thank you, Naveed. And also just wanted to say papers are on our website. So if you're interested, you can download it. And if you have questions, just shoot me an email.
okay,
Thank
awesome.
you, Naveed.
Thank you so much. Thank you, everyone. Thanks.
Right. Okay.
Have a good one. Bye.